Okay, so this is going to be the first of a series of video tutorials that's going to be going over your review test and also talking about your upcoming test. So first of all, the format of the test. There's going to be 25 to 30 multiple choice or short answer questions. Some of those will be IB style, some of them will be AP style, and maybe even some Regent style. And then also the in-class portion will be some free response questions with a few parts. The take-home will be a mix of AP and IB questions, similar format, a few multiple choice, and some free response. So what are the topics on the test? So first of all, we're going to be talking about the basics of motion. So whether you displacement, velocities, accelerations, the difference between velocity and speed, distance and displacement, frame of reference and relative motion, which you'll see a few examples of that in the review packet. The differences between average and instantaneous speed, all of your motion graphs, so your position time, your velocity time, and your acceleration versus time, which is just what I just said right here. So reading the graphs directly, in other words, and knowing exactly what the object's doing. So if I have a position time and there's a constant relationship, what does that mean in terms of the object's motion? And you could translate this for any graph and then any type of linear graph or any sort of curved shape. Calculate and interpret the slope, okay, and then calculate and interpret the area. So we'll be talking about this in the video as well. And then also there may be some changing acceleration graphs, meaning that the acceleration versus time is not constant. So think of something like at an object jumping out of an airplane and reaching terminal velocity. So there's a changing acceleration, although this won't be emphasized. And then the kinematics and freefall. So solving problems in 1 or 2 steps, deriving equations, and then talking about the units of those equations, concepts of freefall, including the effects of air resistance, okay, as I just mentioned just above here. And just to comment on that, you assume air resistance is negligible unless the problem talks about, explicitly states, or discusses implicitly states the presence of air resistance, considering something like terminal velocity. And then there's going to be a lab-based question. This is something new with the AP. So given a scenario, giving a list of equipment, come up with a procedure in order to solve the problem. So this is going to be very much like many of our labs where you make the procedure. All right, so let's get into it. So number 1 is looking at a velocity versus time graph and asked to figure out the acceleration versus time. So the connection here is that the slope of this graph represents the acceleration. So another way of addressing this is asking, what is the slope doing? So I'm going to look at some tangent lines at some various points, and then I'm going to interpret those tangent lines. And generally 3 or 5 slopes kind of give you a good idea of what's happening. So now I see that the slope starts off really steep. It is in the negative direction, so I'm looking for something that starts off negative and a big value, negative and a big value. Okay, so right off the bat, I can eliminate these 2 choices. And then I also see a slope of 0. Okay, so there's a slope of 0, there's a slope of 0. And excuse me, that means that we have a slope of 0. That means my acceleration 0. So that means that the acceleration's got to have a 0 value. But this in-between value is what separates these 2 choices, that I see a constantly decreasing slope. So I'm going to see a constantly decreasing acceleration. Okay, and although this looks like it's an increasing value, if you think about numerically, this is like, let's say, -5. It's sometime later going to be -3, sometime later going to be -1, and then sometime later going to be eventually 0, which is at that point right there. So this is my correct answer. But it's absolutely critical that you know the definition of acceleration based on the fact that this is a velocity versus time. So if I do delta v over delta t, I have my definition of acceleration. All right, number 2. A ball is released from rest on the surface of the moon. Which of the following quantities increases at an increasing rate? So I know that the acceleration due to gravity, is always constant on any planet, whether we're talking about the moon, Jupiter, the Earth, and I just said the moon is a planet. So any big object, actually we could even argue that the acceleration due to gravity around you right now is constant, although it is very small. The velocity we know is increasing, but since the acceleration is constant, the velocity is increasing at a constant rate. So then that leaves my position, the distance that it falls. So my position, since the position is proportional to t squared for accelerating objects, that means that my position time graph looks like a parabola for accelerating objects. That is increasing then at an increasing rate. In other words, if you double the time, you quadruple the distance that it falls. So only the distance that the object has fallen. Number 3, a car is heading east at a speed of 10 meters per second. A bird is flying north at a speed of 4 meters per second. So we want to know which of the following vectors represents the velocity of the bird relative to a person in the car. So we want to know the velocity of the bird relative to someone in the car. So if you recall, when we're talking about relative motion, we need to have a common reference frame. Both of these velocities, what's important for you to realize is that these velocities are relative to the ground. So what I want to know is the velocity of the bird relative to the ground, and I'm going to add that to the velocity of the ground relative to the car. Now, what's important is that we know that this vector is going in the exact same direction as the bird, because that's how it's described. But this vector, the velocity of the ground relative to the car, you can imagine if you were like standing right here, if you were on the ground standing right here, if the car's coming at you, okay, the ground if this is the velocity of the car relative to the ground, if you were in the car, what you would see is that the ground is moving towards you. So what we have here is we have these two vectors, arrows, that are being added, and all I want to do is now connect them tip to tail, so the two red vectors. So I'm going to redraw my first vector. I'm going to draw the velocity of the ground relative to the car, and then my resultant will be the hypotenuse. It's a very bad hypotenuse, but we get an idea of the direction, which would be this choice right here, going up to the left. .5, we have two stones, X and Y, of different masses are dropped from the top of a cliff. Stone Y is dropped from short time after stone X. Air resistance is negligible. So we have a situation where one object is dropped a little bit before the second object. And so we want to know, while the stones are falling, the distance between them. So if we take a look at these choices, if we want to know what's happening to the distance between them, we look at these first few choices. It's comparing the masses of the two objects, and what we know is that regardless of the mass, the acceleration of the two objects is constant. Okay, so even if the mass of y is greater than the mass of x, the acceleration of the two masses is constant. So any one of these that talks about the difference of the masses have anything to do with it, are incorrect. So now we want to know whether or not the distance between them is growing or shrinking. And it turns out that you can actually kind of see this, that delta x is equal to v naught t plus 1/2 a t squared. That basically one of the stones has a head start. Okay, so the instant that the second stone is dropped, which starts off at rest, the first stone has some initial velocity. So 1 second later, it's going to increase its distance that it falls by this v naught t. So every second after that, since the first stone has some initial velocity, it's going to get bigger by this v naught t. So the distance between them increases every second, whether the mass of x is greater or less than the mass of y. Like I said, the mass does not affect the acceleration of an object in freefall. So it increases. Choice D. Number 5, a ball is dropped at a time t equals 0 on a horizontal surface from which it rebounds. Which of the following graphs shows the variation of speed, okay, of that ball? So first of all, we want to know speed is a scalar. And what that means is we don't talk about it in terms of negative speed. So we know that the speed is going to increase on its way down. So that actually eliminates 2 choices down here, because what we see on either of these graphs is the speed starting off at a big value and then getting smaller. So now it's a question of whether or not we have these 2 graphs. And what if you notice is that the slope of this one right here and the slope on the first side and the slope on the second side, those 2 look about the same slope. And so that would imply that it's speeding up at the same rate at which it's slowing down. And you can imagine if you have an object that is hitting the ground, okay, that acceleration is going to have to be different than the acceleration at which it's speeding up. In other words, the rate at which it slows down, okay, this is going to be a bigger acceleration. And you can imagine that the ball hitting the ground is going to be a bigger acceleration than which it speeds up. So this is our correct choice, where the slope of this part, since this is speed versus time, is the acceleration due to gravity, g. And then this acceleration is the stopping acceleration of the ball on contact with the floor. The next is a definition of an area. This is a VT graph, and we're asked to find what is the area between the line and the time axis. And you could always use units to help you out. When you find area, you're always multiplying the 2 axes. So if you take a meter per second and I multiply it by a second, what we can see is that the seconds cancel out and I'm left with a unit of a meter. So even if you don't remember, and this is something you certainly can, that the area under the VT graph is a displacement, you can actually do some dimensional analysis in order to figure that out on the spot. So the correct answer is B, the displacement of the object. Number 7, which of the following is the correct definition of an average acceleration? Well, since acceleration is a vector, it's got to have a vector in its definition. So we have a change in velocity. So it's not just the velocity divided by time taken, it's the change in velocity divided by the time taken. Because you can imagine that if something's going along at a constant speed, the acceleration by definition must be 0. So we want to do a change in velocity. So if I'm going along at 3 meters per second and sometime later I have a velocity of 3 meters per second, my change in velocity is 0, and that would reflect in this definition here. Okay, so in this scenario, we're given the displacement of a car, which the IB uses the symbol S for displacement. Okay, the AP uses X, or better yet, delta X, a change in position. And then we want to know which time interval the speed is greatest. So basically what I want to look at is what time interval is the slope the steepest. Okay, and since we're talking about speed, we don't care about whether it is positive or negative, but if we actually look, that this looks about the same unit of time as that, and so if that's the case, then we're just looking at in which case has the greater change in position, which if you look at the distance there and you look at the distance there, over here on A is greater. So that's actually the steeper slope. But once again, recognizing that this is referring to slope, then this becomes a much easier problem. Number 9, we want to know which area, S1, S2, S3, or combination areas represents the total distance moved by the car during the time the speed is reducing. So if we look, this is the speed of the car, okay? And so I see a decreasing speed in this S1 because it starts off at some speed here, and then sometime later it's some speed there. And then it's going along at a constant speed, and then it's decreasing once again. So I see my one area S1, and then I see my second area S3, and we get, which one is that? S1 and S3. So that's choice C right here. All right, number 11. That's right, there's no number 10. A ball is thrown vertically upwards to the ground. The graph shows the variation of time with the vertical displacement. Which of the following gives the final displacement after t, a time of t, and the average speed between the time t0 and t equals t? So if we want to figure out the displacement, okay, the displacement of this object, it starts off at 0 and then ends off at 0. So the change in position, which is the definition of displacement, is 0. If you start and end at the same spot, then your displacement's 0. So we could actually eliminate choice C, and then although we can't see it, we can eliminate choice D. Now the average speed, now since speed is a scalar, the average speed is the total distance traveled, which would be, it moves up d, so it moves up distance d, and then moves back a distance d. So the distance traveled is 2d, and we divide it by the time. So average speed is total distance divided by total time. So we get our choice B. The next one shows a graph of how the quantity y varies with time of a falling object. Okay, so our quantity y is our vertical distance. And we'll talk more about this with projectile motion. So which of the following quantities could be represented by y? Okay. Oh, I'm sorry. This is just some unknown quantity. We don't. So okay. So we don't know that this is the vertical distance. So forget that. Okay, so which of the following quantities could be represented by y? So we know it's a falling object, right? And we know an object's speed is going to increase. And its position would look more like a squared graph because it's increasing position at an increasing rate, which we don't really see right here. We know that its acceleration, at least for the first part, might be constant, and then if we're including air resistance, might taper off. But in this case, what we know is that the speed is increasing. Okay, so this looks like a good candidate for speed. And if we neglect air resistance, we would expect that the speed to continuously increase. But since we see this like tapering off, this looks like a perfect scenario where we're reaching terminal velocity, where the velocity is not changing with respect to time. So this is actually speed when air resistance is not negligible. And speaking of negligible, this just means like it could be like ignored. So if I say the air resistance is negligible, then that means that the value is either we're not accounting for it, or it's so small that it doesn't influence our results. So not negligible meaning it isn't being included. So number 14, initial speed u and acceleration a after time t, the final speed is v. The average speed of the object can be expressed. So this is just like any definition of average. So we have two speeds, u and v, and if I want to figure out the average speed, which we want to probably put a v bar, it's just you add them up and divide by 2. So which condition is necessary for the equation to apply? Now the only way that this can work, if I look at my vt graph, is that, you know, if I consider, like, let's say I'm going along at some speed, and then I have a sharp bump, and then I go along at some speed, but I go along at that speed for a long period of time, I simply can't just average the final speed and add it up with the initial speed and then divide by 2, because you can kind of imagine that I'm traveling along at this final speed for a much greater time. So therefore, my average has to be closer to this. So the only way that you could just simply average two speeds is if the slope of that graph stays constant. So if I look at a VT graph, if the slope of this graph stays constant, then I could simply take what is the speed at the end, what is the speed at the beginning, add them up, divide by 2. So what does this tell me about the object's motion is that I could recognize that the slope of this graph is staying constant, and since the slope of this graph represents acceleration, I know that the acceleration must be constant. So that must be right here, choice A. The acceleration must be constant. The graph below shows the variation of time t of the acceleration a from an object t0 to tt. Okay, so we have an acceleration versus time. So once again, we're going to use some units to help us recognize what the area is. Once again, area, we're taking the y units, so in this case acceleration is meters over second squared, and we're multiplying it by the x units, in this case time, so seconds. And so when you take a meter per second squared and you multiply it by a second, you end up with a unit of meters per second. Now, the thing that we have to tell here is that that eliminates two of the choices. And since we're taking an acceleration and we're multiplying it by a time, then what we know is that acceleration is equal to a change in velocity over time. So if I multiply at, I don't just get an average velocity, I get a changing velocity. So the area underneath a acceleration time graph represents the change in velocity. All right, so this one is a little bit longer, and actually we're going to start this problem on the next video. So take a look at part 2 of our review for kinematics and freefall, and we'll start up there. All right, thank you.